Hello, pre-calc honor students. Here are with 10.4, our last section in this chapter 10, solving trigonometric equations. These are going to be much trickier than the ones we had before. But first, a little example problem. Gravity is the driving force for waterfalls, but gravitational acceleration varies over the surface of our planet. And not by much, but because the Earth is somewhat squashed, it's not a perfect sphere, you don't have the same distance from the center everywhere. So here's the equation. It's an approximation equation. It involves sine of theta and squarings and so forth. And I graphed it on GeoGebra, and you can see that slight variation here. Do you sense a little symmetry here? Well, yeah. What do you think? Sure, even symmetry. And, you might think, well, oh, the sine is odd, though, Mr. Ling. But, oh, careful, it's a sine squared, which could be thought of as 1 minus cosine squared. And the even cosine function squared will still make it even. Sine squared of 2 theta, 2. You can replace that with 1 minus cosine squared 2 theta, and then you're still looking at an even function. So that's why this ended up even. And what happens, we're going to find out this, but another quick question. What happens at the equator? At the equator, you get your lowest gravitational acceleration because that's where the Earth is bulging out the most. Okay, now, when is g equal to 9.8 meters per second squared? Because I know a lot of you use that approximation, but it really only happens at one parallel, and we're going to come back at the end of the lesson to figure out what that is. Okay, so let's pause. And here are our methods for solving trig equations in the form f of x equals g of x. Method 1 is to use a graphing calculator or GeoGebra to graph y equals f of x and y equals g of x on the same set of axes. Find the points of intersection with zoom and trace or the intersection feature of your graphing utility. The thing is, though, you will not have problems like this on the Chapter 10 test since calculators are not allowed. But it will most likely show up on the exam and the AP exams next year. So be ready for that, kids. Method 2 now is use these guidelines to solve these equations without a calculator. Well, it may be helpful to draw a quick sketch of the two functions, of the two sides of the graph, to see where the solutions are, to see where they intersect. And if the equation involves both functions of 2x and x, be consistent. Change the 2x ones into x by using your double angle identities. Now, if the equation only involves functions of 2x, then you can just solve it in 2x directly and then solve for x. And we'll have an example of that later. Be careful not to lose roots. You can't divide both sides of the equation by the variable. You'll tend to lose roots. So here's our example 1. Cosine 2x equals 1 minus sine x. Let's solve from 0 to 2 pi. I put just some typical sketch paper on here because I want you to be able to do this without the calculator to come up with a quick sketch to see what's going on here. Well, let's look at our blue function first. Cosine 2x is the left side of the equation. From 0 to 2 pi, normally we get one cycle at 0, and all these key points. But since we have a 2 inside here, we double the frequency. So the cosine is going to go mama, but it's going to have one complete cycle from 0 to pi. So it's going to be pretty intense like this. And then a whole nother cycle in here. Okay? 2 complete cycles of the cosine wave. Now let's look at our sine graph, 1 minus sine. Well, the sine is normally like this, and we're going to flip it over the y, and then we're going to raise it up 1. So it's going to go through 0 to get you up to 1. But then it's going to come down to pi over 2, then back up to pi, up to 2, and then back down here again. And so we can see we're going to get a few answers here, and we actually sort of bumped into 3 answers right there, 0, pi, and 2 pi. But it also looks like we get some answers in here that we should look for and expect when we do our solution, or a more precise solution here, using our trig identities. Now, here's where it gets tricky. You got cosine 2x, and you got 3 choices for expanding that. So I would go with the one that keeps it in sine. So let's choose the one that goes 1 minus 2 sine squared of x equals 1 minus sine x. That is pretty handy, because now we got everything in just sine x. The ones cancel from both sides, so I get negative 2 sine squared x equals negative sine x. Don't divide by sine x. You're going to lose those roots. Instead, we add a sine x to both sides, factor out a sine x, making negative 2 sine x plus 1 equals 0. And so we get the sine x equals 0, or negative 2 sine x plus 1 equals 0, and that leads to sine x equals a half. From this, then, you get two solutions. Just switch to double page for a second here. You get the sine x equals 0. That happens here at 0 and pi and 2 pi. And those are the ones we saw. The sine x equals a half. Get our unit circle out here when it is equal to half. Here in the first and second quadrant, pi over 6 and 5 pi over 6. So there's your solutions at x equals 0, pi over 6, 5 pi over 6, pi, and no reason to say 2 pi because that's coterminal with 0. So there you go. Okay? Now, and notice how that's consistent with, there's our pi over 6, and there's our 5 pi over 6. And there's our 0 and pi. Okay. Let's take a look at another question. Example 2. Solve 3 cosine 2x plus cosine x equals 2 from 0 to 2 pi. This one's a little harder to just do a quick sketch of. And you might just get frustrated trying with all the doubling and tripling and so forth. So instead, I am going to just go right to the algebra and keep it in cosine this time. I'm going to replace the cosine 2x with 2 cosine squared x minus 1 plus cosine x minus 2 equals 0, because eventually I want to factor it and set it each factor equal to 0. So 6 cosine squared x minus 3 plus cosine x minus 2 equals 0. So that's 6 cosine squared x minus, or plus cosine x minus 5 equals 0. I believe this factors. Let's try it. Equals 0. 5 has got to be 5 and 1. And we're going to have a cosine x on both sides. So let's see. 3 and 2. 6 and 1. 6 and 1, yeah. Positive 6 cosine x and a 1 here. And if we make this plus and this minus, there you go. 6 cosine x minus 5. Yeah, minus 5 cosine x plus 6 is 1 cosine x. So you get cosine x equals 5/6, and you also get cosine x equals negative 1. Now this one is something you can do on your calculator. When does the cosine hit negative 1? Back here at pi. X equals pi. That's without a calculator. This one you would need a calculator. When is the cosine 5/6? And you can get one answer by doing inverse cosine of 5/6. And you get 0.59 about. And then the second answer would be negative 0.59. We add 2 pi onto it to get it into the range we're talking about, and you get 5.7. Okay, there you go. So there are your 3 answers for that one. Now, let's see what we can get example 3 here. This example, as I mentioned earlier, when you have just double angle identities and not a single angle identity. So let's see what we can do here. From 0 to 2 pi. First I'm going to do the quick sketch so you can see why we get so many answers. 0 to 2 pi, it's the sine 2x. Also, it's going to go twice as high as normal. So it's going to go up to 2 and down to negative 2. Okay? And we're going to get one cycle from 0 to pi of the sine. So let's further subdivide here. 0 max, 0 min 0. So we're going to get a cycle like that. And then 0 max, 0 min 0, another cycle. Setting that equal to 1 now. Here's our 1 line. Let's get that straight. There we go. Maybe there we go. We can see how many answers to expect. I see answers here, 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 and here. 4 answers to expect. Let's see how that works. How do you get 4 answers? 2 sine 2x equals 1. Well, you know, if you try to expand this into 2 sine x cosine x, you're not going to get something you can factor. It's just not going to work out. So you just say sine 2x equals a half. And when does a sine equal a half? At pi over 6. and 5 pi over 6. But make sure whenever you have a double or triple angle or anything like that, set 2x equal to pi over 6 plus 2 pi n. Or 2x equals 5 pi over 6 plus 2 pi n. But let me do that on the next page. Let's do this one first. Let's split our pages here. Split page, oh, advance. Here goes. For this answer, we get x equals pi over 12 plus pi n. So that's pi over 12, add another pi on, that's 12, that's 13 pi over 12, add another pi on, that's 25 pi over 12, add another pi on, that's 37 pi over 12. Whoa, thanks for holding the bus. We could have stopped there. 24 pi over 12 is plenty. These are in the 0 to 2 pi range. But we also get x equals 2x equals 5 pi over 6 plus 2 pi n. So x equals 5 pi over 12 plus pi n. So that means x equals 5 pi over 12. Add another 12 pi over 12 on, so that's 17 pi over 12. 29 pi over 12. Oh, too much. Too much. So we don't take that answer. And so there's our 4 answers. Oh, oh. There's our 4 answers. Let's circle them. Pi over 12, 13 pi over 12, 5 pi over 12, 17 pi over 12. Consistent with what we saw in our picture. Okay, now let's do one of the homework problems. It's an inequality, and I want to make sure we cover some of these. Tan x is less than 2 sine x for 0 to 2 pi. Now be careful. Some students just go, hoo-dee-doo-dee-doo. They say, oh, tan is sine over cosine. Well, yes, that's great. And then they divide both sides by sine. Divide both sides by sine. They go, ooh, whoosh, whoosh. Let's see where this goes. Then that's 1 over cosine x is less than 2, or cosine x is greater than a half. When is the cosine greater than a half? They're going to get stuff in here and here. But the problem with this is you're divided both sides by sine. You don't know if sine is positive or negative. So you have to go through all this tricky casework to see, did it keep the direction the same or did it invert it? So that's why I don't want you taking this approach. Oh, no, 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 no. Let's just cover that up with rainbows. No, don't do that. Do not divide by the unknown. So our solution approach here is simple. We're going to sketch it. Oh, let go now. Let go. Woo, hang on. Okay. Pause. We're going to sketch it to get a rough idea where we expect the one function to be lower than the other function, and then solve the corresponding equation to find out exact points of the boundaries of what works and doesn't work. So let's try that. You got tan x is less than 2 sine x. Tan x is less than 2 sine x. So let's graph tan x. Y equals tan x from 0 to 2 pi. Well, it equals 0 here at 0, pi, and 2 pi. And remember, pi over 2, the tangent's undefined. And also at 3 pi over 2. So we get these whoosh like that. There's your tangent function. And we can look at that as y1. Now let's look at the other graph. y2 equals 2 sine x. 2 sine x. So that's going to go up to 2 and down to negative 2. 0 max, 0 min 0. And so here's our 2 sine x graph. So we can see we've got some intersecting points here. And what we want to know, we're going to find those by hand. And also over here, right? What we want to know is when is the blue graph below the red graph. So that's in here. That's in here. That's a little bit in here. And that's it. So we have these three separate sections we're going to have to represent. Okay? So, let's take a look. And solve the corresponding equation so we can find out exactly where these things are happening. Okay? Now, solve the corresponding equation. Here we go. Tan x equals 2 sine x. Well, we've got sine x over cosine x equals 2 sine x. Now, we can multiply both sides by cosine x, and we don't have to worry about what the sine of cosine x is because we're not doing an inequality anymore. We have sine x equals 2 sine x cosine x. Let's subtract 2 sine x cosine x from both sides, equal to 0. And now you can factor out a sine x. Leave behind 1 minus 2 cosine x equals 0. So this will happen when sine x equals 0, or when 1 minus 2 cosine x equals 0, that's 1 equals 2 cosine x, that's cosine x equals a half. Well, the sine x is 0 at 0 and pi. And sure enough, those are some of our intersections, also at 2 pi. We also have the cosine of x equaling a half at pi over 3 and 5 pi over 3. Pi over 3 and 5 pi over 3. And that was this one right here. This is pi over 3. And here's our 5 pi over 3 over here in the fourth quadrant. There, we've got all the points now. Now you can represent the answer. I'm going to do this in green. We want to represent this region. That's from 0 is less than, because we want to be strictly less than the thing then. So 0 is less than x, is less than pi over 3. Notice we don't want to include the stuff from pi over 3 on, and we went too high there. But now we have all this stuff. And notice pi over 2 didn't come up as an answer. But pi over 2 is a spot where the tangent is undefined. So you got to be careful just doing this approach. You wouldn't see then that undefined point at pi over 2, and you might think that you just continue on from pi over 3. You don't. So from pi over 2 is less than x is less than pi. And now let's get this little wedge in here. That's from 3 pi over 2 is less than x is less than 5 pi over 3. So these are great problems because they involve taking a look at both the trig functions and doing it by hand, but also looking at a sketch so you understand when is one function below another function. Okay? And we wrap up here. Now let's look back at our G example from way back. So I'm going to go back to the very beginning. We were looking at this, as I recall. Yeah. Here's the equation. Has symmetry. This is for G. And I went ahead and put in GeoGebra, and sure enough, I focused on this area and I set it equal. I took one side of the equation, G equal to 9.8, and the other side of the equation, this in black here, is this original function, and the horizontal line crosses the function in 2 spots. I got these two. You might wonder, why did it 8 prime? Well, I took advantage of the symmetry, and also I kept on doing the solver on this, and it was a little frustrating because I kept clicking on it. It only showed me 1 point because it was finding all sorts of roots way out here because this thing will continue to oscillate. It doesn't know we just have one planet here from -90 to 90 latitude. So let's convert this to degrees, and you get 37 degrees, 37.956 degrees. So that's both north and south of the equator. Where is this? There. Candlestick Park. Look at that. Oh, shoot. Doesn't have the, yeah, it should have the, yeah, there it is. 37 degrees, 42 minutes. Okay. And I just happened to be watching the Saints game at this time. And it looks like Saints 32, San Francisco 29 with 45 seconds. And it's a miracle throw. And he doesn't quite catch it. A little too late. Well, they're going to try again probably. Okay. Flange out.